In today's video, we are going to explore the fascinating life cycle of stars, a journey that begins with an enormous cloud made up of dust and gas, which astronomers refer to as a nebula. Over long periods of time, gravity gradually pulls together these tiny particles of dust and gas, compressing them more and more tightly until a dense structure begins to form, known as a protostar. As additional particles continue to collide and stick to this protostar, it grows in size and mass, which in turn increases its gravitational force, allowing it to attract even more surrounding material. This increase in gravitational pressure compresses the protostar further, making it more compact and increasing its internal temperature. The particles inside become so densely packed that collisions between them become more frequent, which causes the temperature to rise dramatically. Eventually, when the internal pressure and heat are high enough, hydrogen nuclei within the core begin to fuse together to create helium nuclei. This remarkable process is known as nuclear fusion, and it generates vast amounts of energy. This energy is what keeps the core of the developing star incredibly hot. At this stage, we now refer to it as a true star, more specifically, a main sequence star. During the main sequence phase, the outward pressure produced by all the energy released through nuclear fusion balances perfectly against the inward pull of gravity. This state of equilibrium allows the star to remain stable for a very long time, often for several billions of years. Our own sun, for example, is currently in this stage of its life cycle. However, a time comes when the star begins to run out of hydrogen, which serves as its fuel. Without this fuel, the nuclear fusion process can no longer continue, and as a result, gravity starts to take over once again. The star contracts inward into a much smaller and hotter form. This contraction increases both temperature and pressure until a point is reached where nuclear fusion can begin again, but this time it involves the formation of elements heavier than helium, including all the elements up to iron on the periodic table. What happens next depends entirely on the original size of the star. If it began as a small to medium-sized star, similar to our sun, then it will expand into a red giant. If, on the other hand, the star was significantly larger to begin with, then it will become a red supergiant. These two paths diverge and result in different final stages. Let us first consider the smaller red giants. After a relatively short phase, the red giant becomes unstable and starts to lose its outer layers, releasing clouds of dust and gas into space. What remains behind is a hot, dense, solid core that no longer undergoes nuclear fusion. This remnant is known as a white dwarf. White dwarfs shine brightly, appearing white due to the intense heat and energy left over, although they are actually quite small in size. Over time, they cool and dim as they radiate away all their stored energy. Eventually, the white dwarf becomes too cold to emit light and transitions into a black dwarf, a theoretical final state where the star is no longer visible due to the absence of emitted light. Now, going back to the other path for large stars, if the main sequence star was much more massive, it will have evolved into a red supergiant. These enormous stars continue to undergo more cycles of nuclear fusion and can shine extremely brightly during this phase. After going through multiple stages of expansion and contraction, the red supergiant ultimately reaches a point where it can no longer maintain stability and explodes in a phenomenal event known as a supernova. This powerful explosion creates elements heavier than iron and hurls them across space, contributing to the formation of new celestial bodies. What follows the supernova also depends on the size of the original star. If the star was very large, the remaining core becomes an incredibly dense object known as a neutron star. These are small in size but extremely dense, composed almost entirely of neutrons. However, if the original star was truly massive, it may collapse completely under its own gravitational force, resulting in the formation of a black hole. Black holes are so dense and possess such strong gravitational fields that not even light can escape their pull. This is why they appear as completely dark regions or voids in the universe, essentially invisible to direct observation. To summarize the entire life cycle of stars, they are born from large clouds of gas and dust, pulled together by gravity to form a protostar. As temperature and pressure increase, Nuclear fusion ignites and transforms the protostar into a main sequence star. Over billions of years, the star burns its hydrogen fuel and eventually evolves depending on its mass. Smaller stars become red giants, shed their outer layers, turn into white dwarfs, and eventually cool into black dwarfs. Larger stars become red supergiants, explode in supernovae, and depending on their size, either become neutron stars or collapse entirely into black holes. That brings us to the end of today's exploration. If you found this explanation engaging and helpful, feel free to give us a like and subscribe for more educational content. We appreciate your time and look forward to seeing you again very soon.